Hello there, and welcome back to Sleepy Science Stories. I'm so glad you're here tonight. Maybe already lying down, or sitting somewhere quiet, with the day gently behind you. This is your time to unwind, to rest your thoughts, and to drift softly into the wider universe. Take a slow breath in, and let it go. Above you, even now, countless stars are glowing, each one a distant sun. And around many of them, hidden in the darkness, circle other worlds. Some are small and rocky. Some are enormous, made of gas and storms. Some glow faintly in eternal twilight. Others are frozen in. More than 5,000 have been found, and perhaps 100 billion more are waiting. Tonight, we'll wander through those distant systems, slowly, gently, learning and resting as we go. We'll follow the story of how humans learned to find other worlds, how we read the tiny dimming of a star, how we trace invisible orbits from flickers of light. As you listen, you don't need to. They form a constellation of calm. So settle in. Let your breathing match the pulse of the cosmos. And let's begin our journey through exoplanets, the search for other worlds. For most of history, we believed our sun was unique. For thousands of years, humans looked up at the sky and thought the sun was unlike any other light. It rose and fell in perfect rhythm, giving warmth, marking time, nurturing every living thing. To ancient eyes, it wasn't just a star, it was the source, the center of creation itself. The other points of light above seemed eternal. Circling them as we circle ours, that thought changed everything. The sky became larger, deeper, not a ceiling, but a vast ocean of possibilities. Then we learned that stars are suns too, each with burns like our own sun, a fusion engine of hydrogen and helium, bright across unimaginable distances. Billions of them fill our galaxy alone, each one ancient, each one surrounded by its own night sky. Remember, you're seeing thousands of suns. The difference is only distance. The physics, the fire, the story, all the same. A planet orbiting another star is called an exoplanet. Alien fires. For most of human history, their existence was pure speculation, stories whispered by philosophers, poets, and dreamers. But now, exoplanet is a scientific term measured in light. Mean empty. It means unexplored. Somewhere beyond our sight. Light travels from another sun, bends around a small world, and continues on its way, perhaps crossing space for centuries before reaching our eyes. In that faint shimmer, a scientist reads the pulse of another system, another dawn. The first exoplanet was confirmed in 1992, orbiting a pulsar. It wasn't orbiting a bright, golden sun like ours, but a dead one. A pulsar is the corpse of a star, spinning rapidly, beaming out radio waves like a cosmic lighthouse. Around one such object, called PSR B1257+12, astronomers found tiny worlds, rocky remnants orbiting a ghost. It was the opposite of what we imagined. Life couldn't exist there. Yet the discovery meant something even greater. Planets could. Imagination. Before 1992, no one had proof of other worlds. Only stories. Writers and scientists dreamed of distant Earths, sometimes with oceans, sometimes with monsters, sometimes with life so. But imagination kept the question alive. Maybe, just maybe, the night sky was full of other homes. It was faith in curiosity itself, the belief that the unknown is never empty. Astronomers long. Thousands upon thousands of candidates. Statistically, there are likely more planets than stars. That means in our galaxy alone, over 100 billion suns, there could be hundreds of billions of worlds. The universe, it seems, is efficient in creation. It makes stars, and then, naturally, it makes planets to accompany them. The cosmos builds company, not isolation. Every dot of light in the night sky could host worlds. The next time you step outside on a clear night, look up and pick a star. That tiny glimmer could be surrounded by planets, some large, some small, perhaps even one like ours. Light takes years, centuries, or millennia to reach us, so the worlds around those stars may have changed or even vanished by now. But the light carries their memory. Every star is a solar. The diversity among exoplanets is breathtaking. Some are huge and stormy, like Jupiter, wrapped in clouds of ammonia and hydrogen. Others are small and hard, like Earth or Mars. There are even classes of planets we don't have here, super-Earths with dense atmospheres, mini-Neptunes with shimmering haze. Every discovery redefines what a planet can be. Some have winds faster than sound. Some may have liquid oceans of methane or molten rock. If you could stand on their surfaces, if they even have surfaces, you'd see suns of strange colors rising and setting across alien skies. Some circle two suns, others drift alone in the dark. Binary systems are common in the galaxy, pairs of stars locked together, dancing for eternity. Some exoplanets orbit both suns at once, experiencing double daylight and twin shadows. Imagine two sunsets painting the sky in gold and red. Yet others are completely unbound. Rogue planets, worldlets flung away from their stars, wander through interstellar darkness, frozen, lightless, alone. They still drift, their gravity intact, their motion eternal. Even in isolation, they remain part of the cosmic order, proving that even loneliness has a place in the universe. Each one has its own rhythm, its own year, its own sunrise. Every planet's orbit creates a unique pattern of time. Some complete a year in just a few hours. Yet each follows the same laws: orbit, spin, light, shadow, cosmic rhythm, repeated endlessly across the galaxy. Every sunrise, no matter how distant, is a moment of rebirth, proof that their year lasts a few days. These worlds skim dangerously near their stars, locked in searing heat. Their orbits are so tight that gravity stretches them into teardrop shapes. Some may even lose their atmospheres, boiled away into glowing tails. From space, they look like comets more than planets. Yet they persist, their motion stable, their existence defiant. They remind us that the dark, their years could last longer than human civilization. If anyone could live there, they'd never see a second summer. Time itself would move differently, patient, vast, unhurried. Others frozen in eternal night. Between the extremes of fire and ice lies a spectrum of worlds. Some are blasted by radiation, glowing red with heat. Others are locked in deep freeze. Both burn and shimmer with equal beauty. Each state, each temperature, is simply another way the cosmos expresses diversity. Yet all are bound by the same cosmic rules. No matter how different they appear, every planet follows the same universal laws. Gravity pulls, light travels, time unfolds. Whether a world is rich in water or rock, gas or dust, it dances to the same equations. The cosmos may seem chaotic, but underneath it all is symmetry, an elegant structure holding everything together. When you realize that, it feels less like cold math and more like quiet music, a harmony that stretches from our world to the edge of everything. Gravity, light, and time connect them and us. Gravity holds the stars. Light tells their story. Time gives it meaning. The search for exoplanets is also a search for ourselves. To look for other worlds is to ask, what makes ours special? Every new planet discovered deepens our sense of context, where we fit, what life requires, and how fragile existence can be. The search isn't only about distance or data, it's about identity. We are explorers not because we need to leave Earth, but because we long to. Astronomy is an act of reflection. When we gaze into the darkness and chart other suns, we are tracing the outline of our own story. The farther we look, the more connected we become, not smaller. See, to look outward is to look inward, and to realize that wonder itself is our home. Most exoplanets are too faint to see directly. Even the largest planets, orbiting the brightest stars, vanish in the glare of their suns. From our point of view, they are invisible, their light drowned out 1 billion times over. Imagine trying to see a candle beside a floodlight from thousands of miles away. The contrast is overwhelming. Yet astronomers knew they had to find a way. If planets couldn't be seen, they could be felt, through the way they tug, dim, or echo through their stars. Discovery, then, became a matter not of sight, but of listening to light itself. Astronomers had to learn to detect them indirectly, so they began to watch the stars, not for what they showed. Mathematical and poetic all at once. Like tracing the outline of an invisible dancer by the movement of shadows, astronomers learned to read what was missing. This is how exoplanets were first revealed, not by sight, but by inference, by the quiet fingerprints they leave upon their suns. One key method is called the transit method. The transit method is among the most elegant ideas in modern astronomy. It relies on the simple geometry of an eclipse. When a planet passes between its star and our eyes, it blocks a tiny fraction of the starlight, usually less than 1%. Steady light that suddenly dims, not by much, but enough to notice if you're patient. That's what happens during a transit. The planet's silhouette, unseen directly, creates a signature curve in the less than the flicker of a candle. Yet that shadow changes everything. It means the planet has a predictable path, a measurable rhythm, a story. From this alone, scientists can model its distance, its year, and sometimes its temperature. The data becomes a kind of portrait, drawn in the language of light and time. A shadow may be brief, but in that briefness lies proof of another world. It gazed at a single patch of sky, observing more than 150,000 stars at once. For years, it recorded their brightness every few minutes, searching for the tiniest changes. Most stars never blinked, but a few did, and those were enough. Out of billions of data points emerged thousands of planets. Kepler transformed patience into discovery, turning silence into a map of worlds. Each dip means a world. Each small downward curve on Kepler's graphs wasn't just a data anomaly, it was a sunrise somewhere else. A planet, solid or gaseous, orbiting its sun, casting that faint, periodic dimming. Every dip had a rhythm, repeating every few days, weeks, or months. From repetition came certainty. From certainty came wonder. Thousands of dips, thousands of worlds, each invisible, yet undeniable. The light of the cosmos had begun to speak in pulses of shadow, and we finally knew how to listen. Another method is radial velocity, the wobble of the star. The radial velocity method came before Kepler, and it remains one of the most sensitive techniques we have. When a planet orbits a star, the star doesn't stay perfectly still. It moves slightly in response, pulled by the planet's gravity. To us, that movement causes the starlight to shift back and forth in color, like the sound of a passing siren. By measuring these shifts, astronomers can infer the planets. It's a dance, the star and planet circling a shared center of gravity. The planet moves fast, the star barely sways. Yet that sway is enough to be measured. For massive planets close to their stars, the tug is strong. For small, distant ones, it's delicate, almost imperceptible. Still, even the faintest wobble leaves a trace in the spectrum of starlight. To detect it is to sense motion. Without movement, to feel gravity through photons. The cosmos, it seems, waltzes in invisible rhythm. That tug creates a rhythm in the starlight's color. When the star moves toward us, its light shifts slightly toward blue. When it moves away, the light drifts toward red. This is the Doppler effect, the same principle that makes a train whistle change pitch as it passes by. By measuring these subtle shifts, astronomers can map the orbit's period and amplitude. Each wave of color is a pulse of gravity. The The star's light becomes a song, and the planet's orbit, its melody. Fall. To the trained eye, it sings of orbits, masses, and resonance. Some stars have multiple peaks, indicating multiple planets, each contributing its own tempo. It's not an exaggeration to say. Astronomers hear the structure of solar systems through these oscillations. The universe hums softly in numbers, and those who learn its rhythm can find planets hidden within its harmony. Some use gravitational microlensing, a cosmic magnifying effect. This method is rarer, but breathtaking in its simplicity. When a massive object, like a star, passes in front of another, perfectly to reveal a hidden world. It's like catching a reflection in a ripple, fleeting, beautiful, and gone. Microlensing proves that even gravity itself can be used as a lens to glimpse the unseen. Even Einstein predicted it. Einstein's theory of general relativity described how mass bends space and time. He likely never imagined it would one day help us find planets around other stars. Yet his equations, written a century ago, underpin this very technique. Light does not travel straight. It curves around gravity wells. So when we observe a distant alignment of stars, makes excellent starlight music. Others use direct imaging, filtering starlight to reveal the faint glow beside it. The rarest and most dramatic discoveries come from direct imaging, actually. Photographing an exoplanet. To do this, astronomers must block out the blinding light of the host star using coronagraphs or special optical tricks. What remains is the faint, ghostly glow of a planet itself, often seen in infrared. These images are grainy, pixelated, yet they hold indescribable beauty. Each one is a genuine picture of another world, a dot of light that is not a star, but a planet shining in its own reflected dawn. It's like spotting a firefly beside a lighthouse. That's how astronomers describe the challenge of direct imaging. The contrast between the planets. Light and its stars' glare can be millions to one. Yet with the right technology, patience, and processing, the firefly can be found. Adaptive optics sharpen the image, algorithms subtract the noise. What's left is a tiny spark in the dark, proof that persistence can make even the faintest glow visible. Each of these glimpses feels miraculous, not because it's unexpected, but because it confirms our quiet belief that even in overwhelming light, something gentle can still shine through. Each method adds another piece to the puzzle. No single technique can reveal everything. Each one provides part of the truth, the size, the mass, the orbit, the atmosphere. Like assembling a mosaic, astronomers combine data from transits, wobbles, and light curves until a world takes shape. The process is slow, cumulative, and deeply human. Discovery doesn't come from sudden revelation, but from careful layering of small certainties. Piece by piece, planet by planet, the puzzle of the galaxy unfolds. Together, they confirm what once seemed impossible. Once, the idea of detecting a planet across light years seemed absurd. Today, it's routine. Dozens are found. Invisible is now measurable. What was once myth has become map. The impossible has simply learned to whisper in numbers. The galaxy is full of planets, and they are everywhere. From hot giants hugging their stars to cold wanderers adrift in the void, the variety is staggering. Every survey deepens the realization. Planets are not rare decorations. They are inevitable outcomes of star formation. The dust that forms a star naturally spins into disks, and those disks birth planets. The universe doesn't make stars alone. It builds families. Every light in the night sky might hold companions, circling in quiet, endless motion. Even small stars may host multiple worlds. The smallest stars, cool, dim red dwarfs, often have tightly packed systems of planets. Some host 5, 6, or even 7 worlds within orbits smaller than Mercury's. Their stars burn slowly, for trillions of years, giving their planets immense time to evolve. Many of the most promising Earth-like candidates orbit such red dwarfs. Their light may be faint, their warmth subtle, but their potential is vast. In the quietest corners of the galaxy, life may be waiting under the soft red glow of these eternal suns. Discovery has become our new starlight. Once, the stars were silent. Now they speak, not in myths, but in data, patterns, and pulses. Each discovery shines like a spark of knowledge against the canvas of night. We no longer need to wonder if other worlds exist. We need only to ask how many and what they're like. Discovery itself has become illumination, a new kind of. A quiet vessel was sent into the dark. Its name was Kepler, a tribute to Johannes Kepler, the astronomer who first described how planets move in ellipses. Unlike the telescopes that scanned wide, for years, it floated in silence, orbiting the sun, collecting faint traces of light. It wasn't looking for beauty, it was looking for rhythm. And in that rhythm, it found entire worlds. It watched over 150,000 stars continuously. Day after day, Kepler's camera stared at a small patch of sky near the constellations Cygnus and Lyra. That patch covered less than 1/400th of the night sky, a tiny fraction. Yet within it were over 150,000 stars, each one monitored continuously. Kepler measured their brightness every half hour, building an archive of numbers that grew like a heartbeat chart for the galaxy. To most eyes, those numbers would look meaningless. To astronomers, they were alive. Each tiny fluctuation a potential sign of another world turning in the dark. For 4 years, it never blinked. Imagine a single, unwavering gaze, for years long, unbroken by sleep or distraction. That was Kepler. Through solar storms, cosmic rays, and the silence of orbit, it remained steady. It couldn't blink because a single missed moment could mean a lost transit, a lost planet. Its patience was mechanical yet poetic, a mirror of human curiosity extended. Data points. The data came as endless columns of numbers, light curves, timestamps, intensities. Each star produced its own pattern, steady or chaotic. Among them were the smallest dips, 1 part in 700 confirmed planets emerged. Out of the sea of data, patterns began to take shape. Planet after planet was confirmed, more than 2,700 by the time Kepler's main mission ended. Each confirmation was a triumph of patience. Each curve, once meaningless, became a story of gravity and time. These planets ranged from blazing giants to temperate Earth-sized worlds. Many circled stars smaller than the Sun, others orbited distant suns we'd never named. Kepler's discoveries multiplied faster than we could describe them. It had opened a new era, one where the galaxy itself became a catalog of possibilities. Many more candidates still await confirmation. Even after its mission officially ended, Kepler's data continues to live. Thousands of signals remain, potential planets not yet confirmed. Teams around the world still comb through archives, using new algorithms and AI models to separate true worlds from instrumental noise. Each reanalysis reveals new surprises. Planets are everywhere. Almost every star appears to have at least one. Many have several. The galaxy, once thought to be a vast expanse of isolated suns, turned out to be full of solar systems. Stars that a year lasts only days. Warm Neptunes, mid-sized planets wrapped in vaporous skies. Super-Earths, rocky worlds larger than ours, with gravity strong enough to hold dense atmospheres. These were new categories, new species of planets, each expanding the definition of what a world could be. Nature, it turned out, was far more inventive than we'd imagined. Some orbits were tilted, some circular, some chaotic. In our solar system, the planets move in orderly rings, nearly flat and stable. Kepler revealed that this neatness is not universal. Some systems are tilted. Precise mathematical relationships, like notes in a chord. The universe, it seems, doesn't prefer order or chaos. It celebrates both. It showed us planetary systems stranger than fiction. Within Mercury's orbit, what writers dreamed, Kepler confirmed. Reality is stranger and far more beautiful than fantasy ever dared. Some had multiple worlds locked in perfect resonance. In some systems, Kepler discovered an astonishing harmony. 3, 5, even 7 planets orbiting in synchronized rhythms, their years and days locked into integer ratios, like cosmic metronomes. Choreography, written in gravity. The universe, we realize, doesn't just build worlds. It composes symphonies. Some orbits were shorter than a week. A handful of Kepler's planets orbit their stars in less than 7 days. They're so close that the stars fill half their sky, blinding, relentless, unsetting. These worlds endure scorching temperatures, sometimes thousands of degrees hotter than molten rock. Their surfaces may glow red, their atmospheres stripped away by stellar winds. Yet they persist. Even under extremes that would vaporize our Earth, gravity keeps them steady. The cosmos, it seems, values endurance as much as beauty. Others stretched beyond our imagination. Farther out, Kepler found planets whose orbits take hundreds of years to complete. Some move so slowly that, differently, what feels eternal to us may be just one orbit to them. Every discovery expanded our sense of normal. With each new world, our definition of normal shifted. Planets can orbit pulsars. They can share orbits. They can exist where logic once said they couldn't. What was once exceptional became expected. The solar system stopped being the model of the cosmos. It became one variation. Complex. Before Kepler, Earth-like meant one thing: a rocky planet at the right distance from a sun-like star. Now we know it's not that simple. Some planets are Earth-sized but too hot. Some are temperate but orbit tiny red dwarfs. Some have thick atmospheres that trap heat, others have none. Being like Earth isn't just about size or distance. It's about chemistry, weather, magnetism, and time. Kepler showed us that Earth-like doesn't mean Earth twin. It means the possibility of variation, life under different rules. Kepler's field of view was just a patch of sky, a cosmic keyhole. And yet, within that small window, thousands of worlds revealed themselves. The implication is staggering. If that tiny region holds so many, what about the rest of the sky? Kepler showed that hidden within those points of light were entire solar systems, invisible until measured. The discovery reframed the night. Every star, no matter how ordinary, might harbor its own orbiting family. The constellations we memorized as pictures now became maps of possibility. Extrapolated, that means hundreds of billions across the galaxy. From that narrow window of Kepler's view, astronomers estimated that most stars have planets. Scaled up to the Milky Way's 200 billion stars, that means hundreds of billions of worlds. Many of them could be rocky. Millions could orbit within habitable zones. The numbers blur into poetry. More planets than grains of sand, more orbits than heartbeats, more potential homes than we can ever visit. The universe is not empty, it is overflowing. Kepler didn't just find planets. It changed our worldview. Before Kepler, our place in the cosmos felt uncertain, almost lonely. After Kepler, the night became populated. Measurement. Yet somehow, the wonder only deepened. We no longer ask if other worlds exist. We ask, which ones could hold life, and what stories might they tell? The universe became more alive, more populated, more intimate. With every world discovered, the cosmos grew smaller, not in size, but in familiarity. The distances remain vast, but they feel less empty now. When you look up, stars. Hot Jupiters were among the first exoplanets we ever found. giant worlds that orbit perilously close to their suns. Their years last only days. Their skies boil with radiation. Imagine a world the size of Jupiter, yet hugging its star so tightly that it glows faintly red from heat. These are gas giants whose atmospheres swirl at thousands of kilometers per hour. Golden fire. They orbit in just a few days. A year on a hot Jupiter could pass in a weekend. Some complete a full orbit in under 48 hours. If you stood above such a planet, the star would dominate. To dusk. Their motion is constant, relentless, a storm that never ends. These worlds teach us that proximity to a star is both creation and punishment. Their skies are blazing with metallic clouds. Above the burning depths of hot Jupiters, strange weather rules. Instead of water vapor, the clouds are made of silicates, the material of glass and sand, vaporized by the heat. In these skies, molten droplets condense and fall like glass rain. Sodium and iron shimmer in the atmosphere, giving them yellow and blue glows. Spectrographs from telescopes show chemical fingerprints of metals. But larger than our planet. Not all worlds are giants of gas. Some are cousins of Earth, solid and heavy, larger yet familiar. Super-Earths bridge the gap between rocky planets and gas worlds. They may have thick atmospheres, or none at all. Some could be covered in clouds and ocean, but they could have stable climates, long-lived stars, and perhaps, if the chemistry is right, the potential for life. They remind us that Earth is not the only blueprint for habitability, only one version of it. Some have thick atmospheres, others bear rock. Among the super-Earths and mini-worlds, diversity reigns. Some have dense, choking skies, layers of carbon dioxide or methane that trap. And magnetism. A strong magnetic field protects, a close star strips away. Each combination of factors writes a different destiny. In this variety, the universe experiments endlessly, as though testing every possible version of a world. Mini-Neptunes are smaller versions of gas giants. Mini-Neptunes are wrapped in thick atmospheres of hydrogen and helium, smaller than Neptune but larger. System, something between solid and ethereal. They float softly in the spectrum of possibility, proving that planetary design is far more flexible than we ever imagined. Ocean worlds may be covered. Water turns to ice not from cold, but from weight. Beneath that ice, a hidden ocean might circulate, warmed by the planet's core. These ocean worlds could cradle life in liquid darkness, organisms, drifting through chemical tides, glowing faintly in the abyss. They are dreams of reflection, entire planets where every sunrise paints itself across an infinite sea. Some could have icy crusts and deep liquid layers. Not all ocean worlds are warm. Some hide their seas beneath solid shells of ice, like Europa or Enceladus in our own system. Beneath frozen crusts, internal heat keeps water liquid. Geysers burst through the surface, releasing plumes of vapor into space, silent proof that something stirs below. These icy worlds challenge our definition of habitable. Life might thrive, not in sunlight, but in geothermal darkness. It's a reminder that warmth can come from within, not just from above. Rogue planets drift without a sun, lost between stars. Some worlds have no home. Star at all. They've been flung away by gravitational chaos, ejected from their systems to wander interstellar space. These rogue planets drift endlessly, bathed in starlight too faint to warm them. If you stood on one, the sky would never change. Only the distant, frozen sparkle of the galaxy itself. They glow faintly from leftover heat. Even in exile, planets retain the warmth of their formation. Deep within, radioactive decay and slow cooling keep them alive with faint inner fire. Astronomers can sometimes detect this glow in infrared, the planet's body heat radiating into the puffy planets are bloated gas spheres with densities like cotton. Not all giants are heavy. Some are astonishingly light for their size. These are puffy planets, worlds so inflated that they could float in water if such a comparison made sense. Their densities are lower than styrofoam, their atmospheres swollen by intense heat. They orbit close to their stars, where energy expands there. Gaseous layers like balloons. From space, they appear delicate, shimmering, fragile, as if one touch could make them collapse. Yet gravity holds them firm. They are paradoxes, immense, yet insubstantial. Some worlds rain glass, iron, or gemstones. Weather, on alien worlds, takes on impossible forms. On one planet, winds blow sideways at thousands of kilometers per hour, carrying shards of glass that slice through the air. On another, iron condenses in the upper atmosphere and falls as molten metal. There are worlds rich in carbon where diamonds may crystallize in. And precise. Lava planets orbit so close they melt continuously. There are worlds where rock itself becomes liquid. These lava planets face their suns so closely that their surfaces glow orange-red. Oceans of molten stone stretching to the horizon. Mountains melt and reform in slow waves. The air is thick with vaporized minerals, a metallic mist that reflects light like a mirror. At night, if there were night, the horizon would glow from within. To see one is to watch geology in motion, a planet alive not with life, but with fire. Others are frozen solid, eternal winters of nitrogen. Nothing melts there. Mountains are frozen waves. Plains are glassy deserts of solid gas. Beneath the surface, perhaps, lie ancient oceans, locked away for millions of years. To look upon such a planet is to glimpse the stillness of time, a place where even light moves carefully. Some might have twin sunsets like in fiction. Few images are as iconic as a planet with two suns. Thanks to Kepler, we know such worlds truly exist. Circumbinary planets orbit pairs of stars, watching them rise and set together, their light blending into hues of gold and red. Depending on the orbits, sunsets may overlap or chase each other across the sky. Nights are short, if they exist at all. For any creature that might live there, light would never be just one color, but a duet. Fiction dreamed it first. The universe quietly confirmed it. Others orbit dying stars, bathed in ghostly light. Some planets circle stars at the end of their lives, white dwarfs, neutron stars. Yet even there, beauty persists. The glow of a white dwarf on a nearby planet would look like an eternal twilight. Cool, silent, but strangely peaceful. A few orbit pulsars, dead stars beating with radiation. The first exoplanets ever discovered were found around a pulsar, a neutron star spinning hundreds of times per second, sending out beams of radiation like a cosmic heartbeat. To orbit such a thing seems impossible, yet there they are, small, rocky bodies enduring unimaginable conditions. The radiation would strip any atmosphere instantly. Day and night are meaningless. There. Yet the planets persist, survivors of stellar death, circling a remnant that still sings across the galaxy. Life there would be unimaginable, yet possible in theory. Even in the most hostile conditions, the idea of life refuses to die. Scientists speculate about forms of biology that could survive under radiation, pressure, or chemical extremes. Not carbon-based, perhaps, but silicon, ammonia, or plasma. We can't rule it out. Every discovery widens the definition of possible. If the universe is creative enough to build planets of glass, diamond, and lava, perhaps it's creative enough to spark life in places we'd never expect. The cosmos has more variety than any dream. After studying thousands of exoplanets, scientists now realize that imagination was too small a tool. Reality has outgrown fiction. There are worlds of storm and silence, of oceans and fire, of light and shadow beyond what language can describe. Each planet adds a new note to the cosmic chord, and together they form the melody of diversity. The night sky is not a repetition of sameness. It is an orchestra of endless variation. Every type of world tells a story of formation, chaos, and chance. Each world, whether blazing or frozen, lonely or abundant, is a record of what can happen when gravity meets dust and time. Some were shaped by violence, collisions, and collapse. Others formed gently, growing ring by ring. Every orbit, every tilt, every atmosphere is a signature of chaos resolving into order. The diversity we see is not randomness. It's the universe writing its autobiography in stone and light. And somewhere, among these stories, lies our own, one chapter in an infinite book of worlds. Life, as we know it, needs liquid water. Every search for life, written in water. Wherever liquid water flows, life tends to follow. That's why astronomers look for its signature, the subtle shimmer in reflected light, the spectral fingerprints of vapor or ice. Water means motion, chemistry, possibility. It is not just a liquid. It's a bridge between the physical and the living. Not too hot, not too cold, a delicate range. The conditions for liquid water are fragile. If a planet is too close to its star, oceans boil away into steam. Too far, and they freeze into ice. Between those extremes lies a narrow band where water can remain liquid, not perfectly, not constantly, but enough for life to have a chance. This thin line is the Goldilocks zone, named for balance. In cosmic terms, it's astonishing how small that range is, and how many worlds still manage to find it. Life, it seems, thrives on precision and patience. This range is called the habitable zone. Astronomers call it the habitable zone, the orbital distance where a planet could sustain liquid water on its surface. It is not a guarantee of life, but an invitation to imagine. Within this band, a world has the potential to hold oceans, weather, and atmosphere. All the necessary ingredients for habitability. The idea sounds simple, yet it reshaped how we look at the galaxy. Every time we find a planet in this range, we whisper a quiet question. Small, cool stars. The habitable zone lies close in, where planets may orbit every few days. For massive, hot stars, the zone is farther out, wide, bright, and brief. As such, stars burn quickly. The relationship is a delicate dance between temperature and distance. If we could see these zones drawn in light, the galaxy would appear webbed with glowing rings, each one a possible cradle for life. For the Sun, Earth sits perfectly within it. Our planet occupies a sweet position, not too near, not too far from the Sun. Here, liquid water can exist, climates can stabilize. Shrouded, scorched, silent. A little farther, and it might have frozen like Mars. We live in a thin zone of luck, a cosmic coincidence that allowed everything we know to happen. For smaller stars, the zone is much closer. Red dwarfs, the smallest and most numerous stars in the galaxy, burn cool and long. Their habitable zones lie close, so close that a planet might be tidally locked, showing one face forever to its star. One side in eternal day, one in endless night. Yet even there, life may find a way, in the twilight regions between, where heat and cold meet in balance. These stars live for trillions of years, offering their worlds more time than any sun like ours. The cosmos saves its greatest patience for the smallest fires. For hotter stars, it's farther away. Massive stars blaze fiercely, burning through their fuel in only a few million years. Their habitable zones lie far out, but for life, that time is fleeting. A world might form, find equilibrium, and lose it before life ever begins. Still, these bright stars sculpt the galaxy with their light, spreading heavy elements that future systems will use. They may not host long-lived life themselves. A potentially habitable planet could be an ocean world or a desert. It could have air or be bare rock. Yet even that possibility carries weight. It means we're not searching in vain. Somewhere out there, in the calm light of another sun, may lie a world where rain falls and rivers carve their way toward alien seas. It doesn't mean they are alive, only that they could be. The distinction is crucial. To be habitable is not to be inhabited. Many planets may fall within the right zone, yet remain sterile. No atmosphere, no protection, no chemistry of life. Still, the potential itself is sacred. It reminds us that life requires not certainty, but opportunity. The cosmos provides the conditions. What happens next is mystery. Every potentially habitable planet is a question mark drawn in orbit, silent, waiting for the story to begin. Atmosphere, chemistry, and time also matter. Distance alone is not enough. A planet's atmosphere regulates heat. Life doesn't appear instantly. It evolves, layer by layer, through billions of quiet years. Without a stable atmosphere or a long-lived star, even a perfect orbit is just geometry. The recipe for life needs patience, protection, and persistence. Too much carbon dioxide, and heat becomes deadly. Carbon dioxide is a paradox, both the giver and taker of balance. In the right amount, it warms a planet enough for oceans to remain liquid, but too much turns that blessing into curse. Venus, once possibly temperate, fell victim to this runaway effect. Its clouds now trap heat so efficiently that lead would melt on its surface. A planet's chemistry can seal its fate. Greenhouse gases decide whether a world breathes or burns. Life walks a narrow path between frost and fire, easily lost. The same forces that give life a home can, in time, take it away. The universe is generous, but never careless. Clouds and magnetic fields play their roles too. Clouds reflect sunlight and trap heat, acting as planetary thermostats. Magnetic fields deflect solar winds that would strip atmospheres bare. Together, they keep worlds stable. Without a magnetic field, a planet becomes vulnerable. Its air torn away atom by atom, its oceans left to evaporate. Earth's invisible shield protects us every day, quietly. It hums with energy from the molten core, a planetary heartbeat. They grow brighter, shifting the habitable zone outward. A planet once perfect may become too hot. Another, once frozen, may thaw. Even orbits can drift, moving a world from comfort to crisis. A pause in the dance of evolution and entropy. Some worlds may have life under ice, not on the surface. If surface conditions fail, life may retreat below, on icy planets or moons. Subsurface oceans can persist, warmed by geothermal energy. There, sunlight is replaced by chemistry, microbes feeding on minerals, surviving in the dark. These hidden seas may be more common than. Some moons may be more habitable than planets. In our own solar system, moons like Europa, Enceladus, and Titan show that habitability isn't limited to planets. These satellites orbit giant worlds, warmed by gravitational tides. They have atmospheres, oceans, and even weather. Europa's cracks vent plumes of water vapor. Titan's methane lakes reflect the dim light of Saturn. If life exists, sun, tidal forces can create warmth. Heat doesn't only come from starlight. When a moon orbits close to a massive planet, gravity stretches it, flexing its interior and generating friction. That friction becomes warmth, enough to melt ice, to drive geysers, to keep oceans liquid beneath frozen crusts. This is how Europa and Enceladus remain active, glowing softly with internal fire. We've seen it with our own instruments. Spacecraft like Cassini and Galileo captured plumes erupting from the surfaces of these moons. Water, salts, organic molecules. Beneath kilometers of ice lies an ocean as vast as Earth's. Those plumes are whispers from below, messages from worlds that may harbor something living. They remind us that the search for life is not just outward. Once it meant Earth-like, now it means energy, chemistry, adaptability. We've found life on Earth thriving in boiling vents, acidic pools, frozen deserts. The boundaries keep moving outward. Life and creation is slow. Somewhere, on some distant world, the process may already be beginning. Molecules gathering, oceans stirring, light waiting to find eyes to see it. The universe, in its quiet way, believes in second chances. How do we know if a planet is alive? It's a question older than science, simple to ask, impossible to answer completely. From across light years, certain colors reflects others. Those patterns become stories, written in spectrum and shadow. Life alters its world. It breathes, reacts, balances, leaves chemical fingerprints behind. To know if a planet is alive, we look not for movement, but for imbalance, the subtle contradiction that only biology creates. We look for biosignatures, chemical clues. A biosignature is any measurable sign that could indicate life's presence. On Earth, that might be oxygen from photosynthesis, methane from microbes, or patterns of gas that remain stable only because living things renew them. When we study another planet, we search for similar fingerprints, not proof, but hints. A mixture of gases that shouldn't coexist naturally may betray something active, something breathing. Each molecule, each spectral dip, is a question mark suspended in light. Is this chemistry or life? Oxygen and methane together suggest something unusual. In chemistry, oxygen and methane should destroy each other quickly. If they exist together in large amounts, something must be replenishing them. On Earth, that something is life. Plants producing oxygen, microbes producing methane. Finding both on another world would be like hearing two notes that only make sense when played by the same song. It wouldn't prove life, but it would make silence impossible. Somewhere in that balance could be forests, algae, or processes we've never seen. Alien, but alive. Leaving behind dark lines in the spectrum, the planet's chemical identity card. It's astonishing. From a dimming smaller than 1%, we can infer the presence of clouds, gases, even temperatures. The light that traveled billions of kilometers carries within it the breath of another world. In every photon, there's a fragment of weather, a record of air. Astronomers use spectroscopy to read them. Spectroscopy is the art of decoding light. Every element, every molecule absorbs and emits at specific wavelengths, unique like fingerprints. By studying these patterns, astronomers can tell what a distant planet's atmosphere contains, how hot it is, and whether gases fluctuate over time. It's like listening to the chords of an unseen orchestra, identifying each instrument by tone alone. From faint, flickering starlight, we extract the composition of entire worlds. It's science, yes, but it feels like listening to the universe whisper its secrets. Of creation, to read those codes is to perform a kind of cosmic census, one beam of light at a time. We are learning to scan for life not with ears or eyes, but with patience and precision. Some missions aim to detect photosynthesis colors. If alien plants exist, they might reveal themselves through color. On Earth, chlorophyll reflects green and absorbs red and blue, creating a sharp spectral feature known as the red edge. Astronomers hope that by observing a planet's reflected light, they might spot a similar pattern, or perhaps something entirely different. Tuned to another sun. Purple vegetation, golden forests, infrared leaves. The possibilities are endless. Light, it seems, is not just illumination. It is language, and biology knows how to speak. Plant life on Earth reflects light to avoid overheating. If we ever detect that sharp edge on another planet, it could be the first glimpse of alien photosynthesis. A planetary-scale shimmer of life, adapting to its own star. A signature of energy balanced and harnessed, of ecosystems breathing under alien skies. It would mean that somewhere, light has already learned to feed itself, or something entirely new. We must also remember, life elsewhere may not use chlorophyll at all. It might rely on pigments we've never seen, tuned to absorb different wavelengths. On a world orbiting a red dwarf, vegetation could be black to capture dim light efficiently. Under a blue-white sun, it might gleam silver or violet. Our expectations, shaped by Earth, might blind us to this. Might change with its seasons. As life grows and decays, gases fluctuate. Oxygen rising in one hemisphere's spring, carbon compounds increasing as autumn falls. Observing such cycles from and clouds gather where forests breathe. These feedbacks create patterns, stability amid chaos. If we ever see a planet with irregular but self-balancing climate, storm systems that seem to organize themselves, it might be a sign of something regulating, maintaining, perhaps even thinking. Even the chaos of weather could carry the echo of life's hand. Even city lights, if advanced life exists. Planet's dark side and seeing a grid of faint, consistent illumination, lights that never fade with sunset. It's a romantic idea, but not impossible. The same tools that detect exoplanet atmospheres could one day detect the signatures of civilization, small beacons of curiosity shining back across the void. The idea of technosignatures goes beyond biology. Technosignatures are evidence not of. Scientists have begun to include these in their searches, expanding the definition of discovery. The question evolves, not just is anyone alive out there, but has anyone built, spoken, reached out? Perhaps one day, our own broadcast will be found by another species asking the same. Maybe we'll detect radio waves, lasers, or satellites. For decades, we've listened with instruments like absence of life. It might mean we are early listeners, that civilizations rise and fall in timescales that rarely overlap. The quiet sky is both invitation and reflection, a mirror reminding us how. The right way? The quiet may not be rejection, but rhythm. Every silence has a heartbeat, if you wait long enough. It might just mean time hasn't yet aligned. In cosmic terms, even civilizations may be like flares, brief flashes separated by millennia. Two worlds could thrive and vanish without ever overlapping in time. Perhaps we are broadcasting into emptiness now, but one day, another will rise, find our signal, and wonder about us as we do them. The scale of the galaxy makes patience. Searching for life is also searching for patience. Every telescope, every data file, every mission is an act of waiting. We collect light that left its source centuries ago, hoping it carries something more than photons, perhaps intention. The search teaches humility. We are observers, not controllers. To find life, we must accept vast silence and endless uncertainty. And yet, sign of life beyond Earth, a single anomaly that changes everything. We may not recognize it at first. It may take years to confirm, decades to understand. But it will begin, as all miracles do. Or dreams. Then came 51 Pegasi b, orbiting a star much like our own. It wasn't what anyone expected, a gas giant, closer to its sun than Mercury is to ours, roasting in perpetual day. Its discovery shattered assumptions and began a new age. For the first time, a world beyond the solar system wasn't just possible. It was real, measurable, and named. Astronomers Michel Mayor and Didier Queloz won the Nobel Prize decades later for that moment of revelation. The cosmos had whispered its first yes. It was a hot Jupiter, shocking scientists in 1995. No one believed a giant planet could orbit so close to its star. Theorists thought gas giants had to form far out, beyond the frost line. Yet 51 Pegasi b circled its star every 4 days. Its skies were boiling. Its clouds metallic, its winds faster than sound. The discovery forced scientists to rewrite the models of planet formation. The universe, it turned out, didn't follow our rules, it wrote its own. And so the term hot Jupiter was born, a reminder that even the most familiar things can exist in unfamiliar ways. Kepler, 22b, one of the first potentially habitable worlds. When Kepler, 22b was discovered, the world took a collective breath. It was the first confirmed planet in a star's habitable zone, about 600 light-years away. It's larger than Earth, likely covered in ocean or cloud. We don't know what it looks like, only that it orbits in that precious range where liquid water could exist. It became a symbol of possibility, a kind of mirror across space. People began to call it a second Earth, not because we knew it was alive, but because we wanted it to be. Kepler 186f, the first Earth-sized planet in the habitable zone. Discovered in 2014, Kepler 186f orbits a dim red. Sunset, skies tinted copper, shadows long and soft. Scientists don't know if it has air or oceans, but it captured our imagination instantly. For the first time, we found a world truly close to our own in size and distance. A faint echo of home, glowing red in another system. Kepler 452b, nicknamed Earth's older cousin. In 2015, Kepler revealed Kepler 452b, a planet 1.6 times the size of. Imagining ancient mountains and oceans that may have come and gone before our own species even existed. It's a glimpse not just outward, but forward, into what Earth itself might look like in the far future, under a brightening sun. TRAPPIST, 1 system, 7 rocky worlds, 3 in the habitable zone. In 2017, astronomers unveiled a wonder, a single red dwarf star, tiny and cool. Orbital resonance, a miniature clockwork solar system. Their skies would show neighboring planets huge and bright, hanging like moons. For dreamers and scientists alike, TRAPPIST-1 is a promise, a system that feels almost like fiction, but is beautifully, perfectly real. A cosmic jewel box, 39 light-years away. Seen from afar, the TRAPPIST-1 system glows like a small cluster of gems orbiting a single ember. Each world has its own density, atmosphere, and color. Some may be oceanic, others rocky and bare. They orbit so closely that a traveler standing on one could watch another rise and set within hours. If any system has the potential for multiple habitable worlds side by side, it's this one. It's as if the universe, in one tiny neighborhood, decided to create a scale model of hope. Cosmic distance is both small and vast, close enough to dream of, far enough to remain unreachable. In astronomical terms, it's next door. In human terms, it's eternity away. Just for. It's practically touching us. Some projects, like Breakthrough Starshot, imagine sending tiny laser-powered probes there within a human lifetime. The first photographs of another planet, taken by machines we built, could be of this world. When we look toward Proxima Centauri at night, we're looking toward our most likely next destination, our first interstellar neighbor. LHS 1140b, a dense world with potential for atmosphere. Discovered in 2017, LHS 1140b orbits a quiet red dwarf star just 40 light-years away. It's a super-Earth, about 1.5 times our. If it indeed has a thick envelope of gases, telescopes like JWST could soon read its chemistry directly. In the silence of space, LHS 1140b feels like a patient world, steady, heavy, and possibly waiting. HD 209458b, first detected with an atmosphere. In 1999, astronomers used the transit method to study HD 209458b, a hot Jupiter 150 light-years away. For the first time, possess a measurable sky. It was a quiet revolution, the first time we read the weather of another world. From that day, astronomy was no longer about points of light. It was about places. It even showed signs of evaporating. Further studies of HD 209458b revealed something haunting, a long, comet-like tail of gas streaming away from the planet. Its atmosphere, heated and torn by year in 1.1 days. Temperatures exceed 2,500 degrees Celsius, hot enough to vaporize metals. The planet is distorted into an egg shape by gravity, and its surface literally melts. Observations show carbon molecules glowing in its atmosphere, forming complex chemistry in the chaos. It's both terrifying and exquisite, a world that teaches us what too close truly means, yet still moves in perfect balance, defying destruction one orbit at a time. GJ1214b, a mysterious water world. This small, warm planet about 40 light-years away may be one of the strangest yet. GJ1214b appears to have a thick atmosphere rich in water vapor. Models suggest it could be an ocean planet, with deep, hot seas and high-pressure ice forming far below. Its sky may be permanently overcast. New, a laboratory of planetary evolution. K2-18b, first with possible water vapor in its sky. When K2-18b was studied by the Hubble Space Telescope, astronomers detected traces of water vapor in its atmosphere, the first for a planet within the habitable zone. It's larger than Earth, smaller than Neptune, orbiting a small, cool star 124 light-years away. The discovery sparked excitement. Water, atmosphere, and temperate climate in one place. Perhaps it's too gaseous for land, but water vapor means clouds, weather, and potential chemistry for life. For the first time, we saw not just a planet, but a sky. TOI 700d, an Earth-sized planet in a calm red dwarf system. TOI 700d orbits a quiet star about 100 light-years away. Discovered by NASA's TESS mission. Analogs we've found. If it has an atmosphere, it could sustain weather, clouds, even rain. For scientists who dream of habitable worlds, it's a rare gift, a place where serenity itself might be there. It orbits blisteringly close to its star, so close that its surface temperature exceeds 1,500 degrees Celsius. Its rock likely melts and resolidifies constantly, forming glowing lakes of lava. It's smaller than Neptune but denser than iron. A world of endurance through heat, carved from stone and gravity alone. Kepler 10b is proof that solid planets exist everywhere, even in the places where no world should survive. Each exoplanet name is a coordinate in human curiosity. They sound cold, strings of letters and numbers. HD 209458b, Kepler 186f, LHS 1140b. Yet behind each is a. Behind each code lies a story. Every exoplanet carries with it the memory of a moment. The first faint dip in brightness, the confirmation email, the cheer in a control room. The story doesn't end there. Years later, another team might revisit the same data, discover a new detail, a moon, an atmosphere. Discovery is cumulative, each generation adding its own chapter. Behind every catalog entry lies not just a planet, but a human heartbeat, a glimpse of wonder at the edge of knowledge. We name them with numbers, but dream of giving them poetry. We may list them as coordinates and catalog codes, but in our hearts, they are myths reborn. Kepler 186f might one day be Aurora. Proxima b could become the nearest dawn. We number them for science, but name them for love. Sky, we start imagining who might be watching us from beneath it. Kepler opened the door, others followed. Kepler was the pioneer, the first great eye that watched the stars without rest. But once its mission ended, the torch didn't go out. It passed from one telescope to another, from orbit to orbit, from generation to generation. Each successor refined the vision, learned from the past, and reached farther. Science, like light, travels onward. The data Kepler left behind became the foundation upon which others now stand. Discovery is not a single moment, it's a continuum. A long breath across decades, whispered through machines that never sleep. TESS, the Transiting Exoplanet Survey Satellite, scans nearly the whole sky. Launched in 2018, TESS became the successor to Kepler's focus stare. Instead of one patch of sky, it surveys nearly the entire celestial dome, one sector at a time. Its mission is to find the nearest, brightest exoplanets, worlds close enough for follow-up studies. Every few weeks, TESS turns its gaze, like a painter shifting canvases, mapping our cosmic neighborhood. Its discoveries are countless: atmospheres with infrared vision. Then came the James Webb Space Telescope, the most powerful observatory ever built. Its golden mirrors unfolded like petals in space, sensitive to infrared light. The heat of ancient stars and distant planets. JWST doesn't just see. It reads warmth itself, decoding the faint signatures of atmospheres light years away. It can detect the breath of methane, the shimmer of carbon dioxide, the sigh of water vapor. When we imagine it staring into the dark, we realize this machine is not cold. It's luminous with purpose, a human dream given perfect focus. Cheops, Plato, and Ariel will refine the search. After Kepler and TESS came New Eyes. Cheops, a mission from Europe to study known exoplanets in detail. Plato, designed to find Earth-like worlds. Planets, but understand them. What is their air made of? Their temperature? Their light? Slowly, the story of other worlds becomes clearer, the language of the cosmos more fluent. Ground telescopes add precision, like the VLT and YLT. While space telescopes soar above the atmosphere, the Earth remains home to giants. The Very Large Telescope, VLT, in Chile, and the upcoming Extremely Large Telescope, YLT, stretch human vision to extraordinary precision. Their mirrors, some wider than a tennis court, gather starlight so faint it barely exists. With adaptive optics and laser guidance, they cancel out the blur of our atmosphere, achieving clarity once thought impossible. These instruments prove that even under our sky, Earth itself can look out and see eternity. Radial velocity. Instruments now detect centimeter-per-second shifts. Precision has reached astonishing levels. Modern spectrographs can measure the motion of a star down to a few centimeters per second, slower than a walking pace. That means they can detect the gravitational tug of an Earth-mass planet orbiting a distant sunday. It's an achievement of almost absurd delicacy, detecting movement smaller than the. We're approaching the sensitivity to find true Earth twins. With every improvement in precision, we get closer to the dream, finding another world truly like ours, similar in size, orbit, and air. Perhaps one evening, an astronomer will look at a new dataset and realize, this one breathes, this one clouds, this one lives. The long wait will end, quietly, beautifully. Data from thousands of light years away flows back to us. Every night, streams of data pour down from orbit. Numbers, images, spectra, gathered from stars thousands of light years distant. Those signals, traveling for centuries through empty space, in their journey on tiny receivers built by human hands. They are transformed into graphs, curves, and colors on computer screens. From that abstract, before us ever could. They are our shared gaze into the unknown, patient and tireless. They remind us that curiosity itself can take shape, and that even machines can be filled with wonder. From a timestamp from a distant moment. The mirror does not judge or alter it. It simply reflects, holds, and focuses. In that gesture, there is something almost spiritual, an act of listening, of receiving. Telescopes are not hunters, but gatherers. They don't chase light, they wait for it. They let the universe come to them, softly. On Earth, adaptive optics cancel out atmospheric blur. The atmosphere that sustains us also blurs our view of the stars. Air shifts, bends light, makes it dance. But astronomers learn to fight back, not with brute force, but with mimicry. When these telescopes open their mirrors, they are like meditating minds, calm, steady, reflecting truth exactly as it is. The vacuum is not emptiness, it's focus. Is the best lens in the universe. Missions often last longer than expected. Many telescopes outlive their planned lifetimes. Hubble was meant to serve for 15 years. It has passed 3 decades. Kepler continued to observe long after its gyroscopes began to fail, reborn as K2. Engineers and scientists coax their instruments through aging, improvising, adapting. These machines become companions, each new day of data a gift. In a way, they live, not biologically, but in purpose, driven by curiosity as enduring as the stars they watch. Engineers treat them like children sent to the stars. When a telescope launches, there's a hush in the control room, a mixture of pride, fear, and love. Engineers have spent years building it, testing it, touching every bolt and panel. Once it leaves Earth, they can no longer hold it. They can only hope. The first signal back is like a heartbeat heard from afar. These machines are our emissaries, our children of metal and light, sent into the dark to see what we cannot. When they end, astronomers mourn quietly. When a mission ends, when fuel runs out, or systems fail, scientists say goodbye in silence. They often hold small ceremonies, watching the last data packet arrive. Some telescopes are left drifting, still orbiting, still reflecting sunlight, now blind but beautiful. There's melancholy in those endings. Instruments go dark, their archives continue to reveal. Students, decades later, reanalyze the numbers and find new patterns, new planets, new truths. Kepler's data alone will yield discoveries for generations discovery. Each generation inherits a deeper map of the cosmos. What once was cutting edge becomes the starting point. Children who watched Hubble's first images now build the telescopes that replace it. Data begets questions, questions beget dreams. Science, like starlight, travels forward, unchanged in essence, but renewed in meaning. The universe gives, we receive. Galaxies as they were billions of years ago, and to glimpse the future, informing stars and emerging worlds. Each one extends our perception a little farther, turns imagination into image. They are prosthetics for wonder, tools for humility. Through them, we finally see that seeing is not just for survival, it's for reverence. Through them, we see ourselves reflected in the dark. When we point a telescope outward, we're really pointing it inward, searching for understanding. The reflection that returns is not just cosmic, it's personal. The universe looks back through the instruments we've made and says, "You are learning to see." They remind us that even machines can dream of light. In their silence, telescopes are dreamers. They don't move or think, yet they exist for. That knowledge is worth the waiting. And in that sense, they are no different from us. Both human and machine, looking up, drawn to brightness, hoping to understand. Even machines, it seems, can dream of light. Are we alone? The question has no age. Before telescopes, before science, even before language, humans looked at the stars and wondered, are we alone? It is a question older than civilization. Whispered in caves, written in myth, carved into constellations. Every age, every culture, every dreamer has felt it. The question is part of us, woven into our consciousness like heartbeat and breath. Whether whispered by ancient firelight or through radio telescopes, it remains the same. Not just curiosity, but longing. a quiet hope that the cosmos might one day whisper back. Civilizations might share the same silence, the same uncertainty, the same yearning. The question becomes a bridge of thought between minds that may never meet. The answer, either way, changes everything. If we find life elsewhere, even a single microbe, it would mean biology is not a miracle but a pattern. The universe, then, is fertile, not indifferent. If we find nothing, whether crowded or empty, the cosmos gains meaning through the way we choose to see it. Life may be common, or unimaginably rare. Statistically, life seems likely. There are billions of stars, trillions of planets, endless combinations of chemistry. But statistics don't breathe, they only suggest. It's possible life blooms easily wherever water flows. It's also possible Earth is a singular miracle, a lone spark in infinite dark. Between probability and silence lies mystery, and that mystery is where all lives. Perhaps life is both common and precious, everywhere and rare at once. A paradox as delicate as existence itself. Perhaps Earth is just one of many gardens. If the galaxy is filled with life, then every star could be a seed, every planet a garden. Some lush, some barren. The thought is comforting, that creation is generous, that life is the natural language of matter. Perhaps the cosmos is not a void, but an immense, quiet garden, still flowering, still learning how to grow. Or perhaps it's the only bloom in cosmic winter. If we are alone, then our responsibility deepens. This single planet, with its forests, oceans, and fragile balance, becomes the universe's irreplaceable. In a cold and endless winter, Earth would be the one candle still burning, fragile but radiant, teaching the universe what it means to feel alive. Some think life is inevitable where it's chemistry's most natural miracle. On countless worlds, those same reactions may already be happening, quietly, invisibly, beyond our reach. If so, the cosmos is not silent, it's simply subtle. Life, like dew, may appear wherever conditions allow, soft, persistent, almost humble in its abundance. Others think it's a miracle that happened once, but others see life as so improbable that it may have occurred only here, once ever. Out of all the collisions, reactions, and randomness of creation, the exact path to consciousness may have unfolded only on this small blue world. It's only storytellers, it's memory. The truth may lie between, probability wrapped in wonder. Perhaps life is neither common nor unique, but scattered, like pearls on a vast dark sea. Rare enough to make finding it a miracle, yet common enough to make believing in it sensible. The truth might be statistical, yet spiritual, numerical, yet poetic. We may never calculate it. We search not only for aliens, but for meaning. Our search for life is also a search for context. We want to know if existence is shared, if consciousness echoes elsewhere. But beneath that is, it would tell us that creation is not indifferent, that it continues to create. When we listen to the stars, we're really listening for companionship. The thought of distant life comforts us. Friendlier. We picture them not as strangers, but as reflections, different in form, similar in longing. Even if we never meet them, just believing they might exist is enough. It softens the silence. It reminds us that awareness is not an accident, but a pattern repeating across infinity. It means the universe shares our story. If life exists elsewhere, then our story is not singular. Stars. We may never hear that song, but knowing it might exist changes the way we listen. It turns loneliness into harmony, distance into belonging. The universe would no longer be background. It would be community. Even if we never meet them, knowing they exist matters. Contact isn't necessary for connection. To know there are others is to feel less fragile, less temporary. It means consciousness is not an isolated phenomenon. It's a property of the universe itself. Perhaps we will never share language or culture, but we share the same physics, the same atoms, the same wonder. That kinship is quiet but profound. We are joined not by proximity, but by existence itself. They would also gaze at stars and ask, who else is out there? It's comforting to imagine that, somewhere far away, another species may be doing what we are doing now. Looking up, asking the same question, listening for a signal. Across the void, two civilizations may be separated by light years, yet united by curiosity. The question itself becomes the bridge. Maybe one day, the echo will close the gap, their question reaching us as our question reaches them. Two halves of the same thought, meeting halfway through the dark. Two civilizations, separated by light years, united by the same curiosity. Curiosity may be the most universal trait of all, more fundamental than to wonder is to care. In that sense, contact has already happened, not through signals or ships, but through shared longing. The light of every question eventually overlaps. Silence may be the universe's way of letting us listen. Perhaps we hear nothing not because no one speaks, but because the universe is giving us space to understand ourselves first. Silence is not emptiness. It's an interval between answers. The quiet sky invites reflection, to notice, to appreciate, to prepare. The cosmos, patient as always, lets us grow into the conversation. Maybe when we're ready, the next sound will arrive, not as a shout, but as a whisper. Patience is part of discovery. The universe unfolds at its own pace. Stars take millions of years to form. Planets take billions to. Like seconds. To search is to wait, and to wait is to believe. Every generation passes the listening onward, knowing that the answer may come long after we are gone, and that is enough. Yet, the more we learn, the more connected we feel. The universe is vast, but not indifferent. It made us capable of noticing. That awareness is its quiet gift, humility as a form of enlightenment. Listening, the building, the waiting, is hope made visible. It's proof that curiosity is stronger than fear, that wonder can endure silence. Whether or not we find others, the search keeps us human. Truth. Our longing to know if life exists elsewhere is itself evidence that the universe is alive through us. We are how the cosmos asks about itself, how it learns its own shape. Every time we look upward, every time we wonder, the universe becomes aware of its own existence. The question, are we alone, has already been answered, not by silence or signal, but by the very fact that we are asking. We are the proof. Each discovered planet orbits in silence. Out there, in the deep, each world moves alone. No sound, no wind, no echo, only motion, constant and pure. Persistence. Every orbit is a heartbeat of the cosmos. Each rotation a meditation on time. Silence, in space, is not absence. It is harmony without noise. Around its star, unseen, it moves forever. Unending rhythm. They rise and set around alien horizons, casting shadows no one sees. Somewhere, a storm rages, an ocean glitters, a mountain cools in twilight. Even without witnesses, the dance continues. Existence, it seems, does not require attention, only balance. A dance no human will ever witness directly. We can measure, model, imagine, but our eyes will never see these sunsets in person. The distances are too vast, the years too many. Yet that doesn't make them less real. There's a strange beauty in knowing that something exists beyond experience, a truth that enough. In astronomy, belief is replaced by evidence, but wonder remains. A dimming of light, a spectral line, a wobble. From these, we know worlds are there. To know is to connect, even from afar. Our knowledge becomes presence. We cannot visit them, but our awareness reaches across light years, bridging the unknown. Knowing is not possession, it's participation, a quiet way of saying we belong to the same sky. Our instruments reach across light years like gentle hands. Telescopes are our fingertips stretched toward infinity. They can't touch, but they can feel through light, through vibration, through the language of data. Each photon they capture is a handshake across centuries. It's astonishing how delicate that touch is, a single particle of light, born from another. Sun, landing softly on a mirror in space. In that fragile contact lies intimacy, a relationship between stars and minds. We map what we cannot touch. Astronomy is cartography of the invisible. We draw maps of systems we will never visit, assign coordinates to the unseen. The maps aren't just geography, they are expressions of faith, diagrams of possibility. Every line, every label says, this exists, even if only as light. Through mapping, we give shape to the formless, turning imagination into knowledge and knowledge into poetry. We name what we cannot see. Numbers, letters, designations, Kepler, 22b, Proxima b, Trappist, 1e. But behind those names are emotions. The thrill of discovery, the ache of distance. To name is to recognize, to bring something into relationship. We cannot see their surfaces, but we can greet them. Naming is how we say hello to the unseen. Somewhere, in the silence, perhaps the universe whispers the names back, in languages older than stars. We imagine warmth on alien soil. When we close our eyes, we picture what we can't observe. Red suns rising over violet oceans, ice plains gleaming beneath twin moons, green skies filled with drifting clouds. We imagine footsteps that may never exist, winds that may never blow. Imagination fills the gap between light and meaning. It's not delusion, it's empathy. In dreaming of alien warmth, we express our own longing for connection. Someday, distant beings may do the same for us. Perhaps somewhere else, under another sky, another intelligence looks outward and wonders about us. They might detect the wobble of our sun, the faint dimming as Earth passes before it. They'll name our world with a code, measure our air, infer our oceans. To them, we'll be a mystery, unseen yet. Upward, they may not know our languages or our sounds, but they'll sense rhythm, the quiet pulse of a planet alive. To them, we'll be the exoplanet, the subject of gentle speculation. The distant dream. To them, Earth will be just another exoplanet. A pale dot orbiting an average star in the Orion arm, its light flickering faintly across space. Nothing about it will seem special. Yet within that dot are oceans, forests, laughter, memory, and thought. To them, we will be just data, a curve, a pattern, a brightness dip. But perhaps they'll feel something deeper, a sense that this one, somehow, it would look serene, eternal. Only up close would they know how delicate it truly is, how much care it requires to remain whole, but perhaps also alive. The spectral lines would whisper oxygen, life, but they would feel it, the improbable order, the sustained imperfection of the living. Perhaps they would pause and listen and realize this world breathes. The light from our world travels outward endlessly. Every second, light from Earth races into space, carrying the image of our blue oceans, our green lands, our clouds in motion. It also carries our radio waves, our music, that we were here, that we looked up, that we cared enough to speak. It carries every song, every thought, every dream. Our collective story, encoded in electromagnetic waves, is already part of the galaxy. Beethoven's symphonies, children's laughter, digital pulses, signals from spacecraft. Even our mistakes travel outward, mixing with starlight. The universe, indifferent yet generous, keeps them all. Someday, someone might capture a fragment and hear our presence, static threaded with melody, numbers tangled with emotion. Every transmission is a message in a cosmic bottle. Adrift but never lost. Maybe someone will hear it, or feel it, Maybe not today, maybe not for eons. But perhaps one day, a distant civilization will tune their instruments and catch a whisper, a pattern that doesn't belong to nature. And they'll know. Someone once lived here, someone once wondered as they do. Maybe they'll replay our light and hear echoes of oceans, thunder, heartbeat. Maybe they'll smile at the thought that life, like light, always finds a way to travel. The search for other worlds is also a search for belonging. We look outward not just to escape, but to understand what it means to be home. Every exoplanet discovered reflects a piece of Earth, its warmth, its danger, its beauty. In searching for others, we discover ourselves. The longing to know who else exists becomes a mirror that shows us what we already are: improbable, resilient, conscious. Belonging is not found elsewhere. It's revealed through the act of seeking. The cosmos is open, that existence is generous enough to allow endless beginnings. We share the same cosmic fabric. The atoms in our bodies were forged in stars, the same kind that shine upon those distant worlds. We are not apart from the universe. We are expressions of it. Every breath we take is made of recycled starlight. The dust that forms new planets once drifted through ancient galaxies, waiting to become eyes, thoughts, awareness. The same laws, the same constants, the same light, connecting everything in one vast continuum. The universe is not something we observe. It is something we are. And that fabric, quietly, endlessly, dreams of life. The universe is in no hurry. It creates, waits, transforms, and creates again. From hydrogen to stars, from dust to every orbit, every spark of thought is part of that dream. And as we drift, silently, within it, we too are dreaming, together, with the stars. And so, we drift again, back toward stillness. The stars fade, not because they end, but because our eyes have rested long enough to remember their light. Out there, 1,000 worlds keep turning. Every orbit, every distant sun, every faint glimmer of life was a mirror reminding us that we, too, are part of this great rhythm. Maybe one day, our own world will be a soft shimmer in someone. Gently now, sleep softly beneath their endless light.